Hello, I'm MC. I'm here to talk about the Tillitis TKey. This is me, hacking a VT100 terminal, as you do. I inherited this thing from Rydis, may he rest in power. This was his hometown, and I think he would have loved having such a conference in his hometown. I'm a member of the technical staff at a small company called Tillitis. We are also located here in Gothenburg. I have a personal website at hack.org, or usually have, because while I'm at the conference, of course, the web server decided to die. But the Tillitis.se website is up and running, so please check it out. Tillitis was born at Mullvad VPN's trustworthy computing research team, but the team split into several companies in 2022 into Glasklar Teknik. They do system transparency and the SIGSON project, and we, Tillitis, we are the hardware department. And as you can see on the picture, this is Cookie, Mullvad's mascot, building some kind of hardware. Foreshadowing here. Joachim Strömmerson presented at foss-north a couple of years ago, and he called the TKey a radically open authentication platform that fits in your pocket. He also said, among other important things, that it's fully open from circuit board to applications and yet provides strong security foundations. We like to call the TKey a small general computer, but it is also an authentication platform. It's a RISC-V computer for sensitive computations. There's no secure enclave, there's no black box. Everything is entirely open. Open licenses, everything from drawings to the chip design, and all the software is available on our repos. And you can read about it and how to develop apps for it on our developer handbook. The TKey can be used for authentication, for digital signatures, maybe as a hardware root of trust in a part of a bigger system, as a signed random number generated with quite good random numbers. You can use it for encryption, and as a protected environment for sensitive computation, because it's a general computer, you can do whatever you like with it. Some advantages of using a TKey is that the client, and the client, that's what we call what you insert the TKey into. The client decides the function of the TKey by feeding it a small program, the device app. So there's usually no need for new hardware for new functionality. You can just choose to run another app. Or you can write your custom app if you like. There's, on the current TKey, no risk for persistent threats of any kind because there is no storage, no persistence whatsoever. The secrets and private keys themselves are not stored on a TKey, they are generated every time, dynamically and deterministically. You can also verify that the TKey comes from the vendor, at least on the locked version for end users. So no one picked it up when it's going through the mail system and changed something with it. You can make your own TKey, or just choose your own base hardware secret if you buy the unlocked version. And maybe if you don't trust us, you can do something like that. Or if you're a big IT department and want to have extreme control of what you hand out to your people. Basic TKey use with our killer app, the agent, the SSH agent we use. Say I want to log into something, say it's a server somewhere, I want to break the glass. I usually use Puppet or Ansible for managing my fleet of servers, but I want to break the glass and log in as root. Or say I want to just talk to GitLab over SSH, or I want to sign my Git commits. Whatever, any usual SSH command, And get support SSH for signing these days too. So I insert the TKey into my client because the agent has already started automatically. And I do some command, SSH to some server. The agent automatically loads the device app signer. It's a small ED2519 signature program into the TKey. The TKey receives a challenge and signs it. It waits to sign it because it wants me to assert presence, like blinking, and I touch the sensor, then it signs it, and I'm in. Just like any other security token, but very, very convenient for SSH. However, this is a general computer, not like a security token at all. How can we trust it? How can we trust it not to leak sensitive material, like the secret key? What if someone writes a malicious app that is designed to leak the secret key? What then? However, what if we don't share anything between the apps and guarantee the software integrity by measuring the apps unconditionally at boot time? And we create new secrets for this combination of the app and this particular device. And these secrets never leave the TKey. So if you use some other app, a malicious app, you get the wrong secret key. And if it leaks that secret key, that's no concern for us. So this is measured boot. You use immutable code in ROM to unconditionally measure the application while it's about to boot. You mix in a hardware secret that is unique per device, and you get a new identity. This is originally an idea from Microsoft Research, and it's similar to TCP's guys. The advantages of using something like this is that the software integrity is guaranteed, and it's also verifiable if the app has a way of exporting the public key and a way of doing challenge response, like our signer, for instance. So this measured identity can be used to create key material. You can base all your key material on this measured identity. The private keys themselves are not stored on the TKey persistently because they are created dynamically every time, which means you also can have an unlimited number of private keys because you can generate more private keys if you like. And these secrets don't leak between device applications because they're forgotten the moment you pull your TKey out from your client. This is very different compared to verified boot, also known as secure boot in the PC world, where you usually have a vendor signing some kind of app and then verifying the signature of the app. This is, of course, unacceptable in an open platform, and that's why we use measured boot instead. So, what is this measured boot, and how do we create the original secret that the app uses? Well, the result of the measured boot is called the compound device identity, and you compute it like this. It's a cryptographic mix of the unique device secret, the secret that is embedded into the hardware design of every TKey. Every TKey has a unique secret. So my device in my pocket has a different secret than yours in your pocket. And then there is an optional user-supplied secret from the user, typically entered interactively, like a passphrase or something. And the measurement, a hash digest over the application itself before it starts. This is the integrity of the application. So this is the combination of something the user has, the device itself, something the user knows, the user's supplied secret, and the integrity of the application. Change one of these three and you get another identity. And as you can see, it's computed like this. So the break2s is a hashtag-less function. That's the CDI. And the CDI itself can be used to create more key material. Inside the TKey, we have a 32-bit RISC-V soft-core processor. We use Clairvoulf's Pico RB32. There's some RAM, not too much of it. There's some memory mapped hardware cores, and we have different firmware mode and application mode. So there's a possibility to access the entire memory space in firmware mode, and in application mode, some of it is locked down. For instance, you can't read out the unique device secret anymore after the application has started. There are no interrupts, so it's very easy to reason about where you are during execution. There's no persistent storage in the released version. However, there is a flash chip on the PCBA, which is useful during development. There's no operating system, just this tiny bootloader firmware. We designed that entire thing with only open source tools because this is all about transparency, and we want to be transparent, radically transparent during the entire process. So all the chip design is done in Verilog, but we use Yosus and the results of the project iStorm, etc., to have a fully open source tooling for the FPGA. This limits our choices of FPGA chips and even PCB manufacturers, but so far our design fits inside a small FPGA, which is fully reversed. Everything is, of course, published. The FPGA chip we have chosen is a Lattice 40, which has good support in open source tools. And crucially for especially the unique device secret, it also has a lockable internal configuration memory. So we can store the entire bit stream, including the firmware and including the ROM, inside the FPGA chip and not read it again. This chip has quite limited resources, but so far we've managed to fit a design. We are willing to pay to reverse other FPGA chips to get something bigger. Inside the FPGA, we have the CPU, some memory of different kinds, a timer, a way of communicating with the client, a touch sensor, and the UDS, the unique device secret, a very good random number generator, and a security monitor, which watches where you are executing at the time, and you can tie down what kind of memory you want to be able to execute and what you don't want to be able to execute. All right. We have some software for this, including an emulator, which I will discuss later, and a simple bootloader, some client applications. I already mentioned the SSH agent, very, very convenient. The TKey verification program is a program you can use to verify that the TKey is unchanged when you get it in the mail. We have TKey Sign, which is compatible with Signify to sign files, verify files, a random number generator, and their corresponding device applications, of course. We have fully support for writing client applications in Go. We also have Python module and Hinode and Java proof of concept. Externally, people have done TypeScript stuff on the client side using web serial, and for implementing device applications, we have so far C libraries and support from LLVM 15 for our CPU architecture, and we've done bring up of the C. We also have some external people who did the same thing on Rust and wrote some device libraries for Rust, the Rusty Key project. We also have initial bring up of Zig, Heineken, and we have packaged many of these things into a TKey builder OSI image you can use with Docker or Podman for ease of development if you don't want to dirty up your own system. The status of this thing is that we have a first official hardware release in March 2023. We have several client apps available for Linux, Mac OS, and Windows. We also have reproducible builds on the FPGA bitstream itself and the firmware for all the TKey device apps, for all the client apps, but not if the target is Mac OS, I'm sorry. The device verification service is up and running, and everything is released and available on GitHub. So let's talk about the emulator. Why do you want an emulator in the first place for a hardware project? Well, it allows a developer of both firmware and device apps to inspect, debug, validate functions, observe memory, and even change stuff in memory during runtime while running real unchanged software. And since our measurement depends on unchanged software, this is really important some of the time. It also allows the chip engineer and the software engineer in combination to experiment with the hardware-software interface and better communicate ideas between the hardware designer and the software developer. These things can be complicated. I mean, a hardware engineer would like to write a beautiful design inside the chip. And then there's an API to this beautiful design, and the API is done to be easy to implement in Verilog or PHDL or something. But how do you use it? Is it simple to use from a software perspective? Who knows? And that's where this comes in. You can experiment with the interface, discuss things, experiment, get a feel. And if it doesn't fit, the software guys, the hardware guys, may be persuaded to change things if they are allowed to try it out before it's designed in an emulator. You can also use it during security audits and testing for security stuff, like verify memory locations and observe internal protocols not visible on the outside of the hardware, which is coming in our next release, for instance. So, we used QEMU, the gold standard of emulators. It's already had support for our architecture. This is RV32 IMC, but our thing is really RV32IM underscore ZMMUL, I think. And that means basically the same thing as RV32 IMC, but we don't have support for division. A bonus was the coming generation of the TKey has flash support in a secure-ish way, and the flash chip was supported in QEMU. We got that for free. That's the best part of open source. We didn't have to do anything, we just added it. So, we had some previous experience using, of course, and slight experience of actually developing inside QEMU, adding things, but not much. And QEMU is huge, it's very complex, and the documentation is there, but not always up to date, yeah. The goal was to always develop new hardware and software interface in the emulator first, experiment with software on top of this interface, get a feeling, as I said, because it's difficult to get a feeling, and write software from specs only. So we also wanted to use it for development of firmware and use it for all development of device and client apps, speaking to the QEMU directly on the same box with no real hardware yet available. In reality, no, it worked fine in the beginning when we didn't have any hardware at all. So enormous payoff in explorative development, very, very good for communication between hardware and software engineers, and very, very good for initial firmware development when we didn't have any hardware. However, it's also sometimes hard to keep up with hardware development because when we actually had something, software had different priorities. We wanted more apps, we wanted libraries, we wanted an SDK, we wanted to bring up other languages. And suddenly we didn't have so much time spending on the QEMU emulator. Yeah. Using the emulator, it looks like this. I'm sorry about this. This is a real command line you have to write to start the QEMU emulating the TKey. Yeah, I know. We have an OCI image for the QEMU as well, and some scripts around it. You can read about it in our development handbook, and it's probably easier to use than just doing like this. But this is how you start QEMU emulating a TKey. Notice this thing in particular. This is how you tell it what firmware you want to load inside it when you start it. This is also important because QEMU itself, it says something about the PTY. And this PTY is important because that's how you speak to the emulated TKey. So when you want to interact with it, you run, for instance, the TKey run app is a client program that just loads a binary, whatever binary, into the TKey, and the firmware automatically measures it and starts it. Notice this important thing. That's the same PTY that QEMU said I was going to use about. That's how you start an application. However, the important stuff is, of course, you want to run GDB against this thing. And QEMU supports the GDB remote protocol if you start it with -s or -big S. So this is how you start GDB interactively running against QEMU, making you use QEMU as a TKey, and you can do whatever you like interactively, like dump memory, check the registers, set breakpoints, change whatever, like you usually do with GDB and GDB debugging. There's some points about using printf debugging, but it's hard to use printf debugging if the only communication channel you have is already taken for communicating with the client app. So this is another communication channel you can use. Notice that when you're actually doing this thing, you feed it the elf. But when you do TQ run up, you feed it the bin. And the bin is a raw binary with no elf headers and no symbols, nothing. But GDB likes its symbols. So QEMU is huge, it moves a lot of stuff happening upstreams. We forked it, it's a friendly fork, we want to be able to upstream our changes. However, priorities means we do other stuff, like focusing on writing actual device apps and client apps instead. So last time we tried to catch up to upstream. Yeah, you consider this PR, that was interesting. Yeah. So, story time. This is going to be slightly embarrassing. And takes some courage, but this is all open information, and we released this as a security bulletin last year in spring, I think. So this is just open and a testimony to our radical transparency, and if you attended Ole's CRA's talk earlier, you know where I'm coming from with this. This is both pro and con QEMU for using an emulator. But anyway, we had a time of check, time of use bug in the signer, found by TKey. And there's a full write-up on this link. You can read all about it if you want. The bug itself is when you send the message to be signed by the signer, you specify the length before sending message. If this length was too large, you received an error back from the signer, but the length you sent initially was still used. Damn. Yeah. So, Sergey, the smart guy, he decided, well, this can leak memory. The exploit is you set increasingly larger size, perhaps just 1 extra byte of the message to sign. Then you send the max message size, which is 4096 bytes. And the first time, then you set the thing to 4097 bytes, for instance. And you send the max size, and you get some already existing memory included in the signature. So the message it signs is what you sent plus 1 byte. Thus, extra byte is unknown, but it's already signed cryptographically inside the T-key by the private key, which means since you have the public key, you can verify this message if you know what that unknown byte is. How do you find out? Well, the byte, that's just 256 values, right? So you iterate over all those possible values, and you verify it. You do an EED 2519 verification on every value until it verifies. Ta-da! Now you know that byte's value. Repeat profit. This leaks memory. Damn! Okay. This is just a time of use, time of change. Style of bug, easy to fix, right? So you just refuse to set the internal size variable if it's too large. Fixed. Right? So we started investigating this thing using the emulator and GDB a lot and some other stuff to find out what are we leaking, because Sergey's initial bug report said, this is a potential leak. I proved that it leaked this much. But if you just continue using this, it takes some time because you have to verify every byte a lot of times. But if you just continue to use it, what happens? What leaks? What is in the memory about the message? So this depends on the order of things in memory. And the order in memory is unknown, so we attached GDB to the QEMU, loaded the signer, checked what's in the memory. So in one of the versions we investigated, the message is on this address, and the secret key is on this address, and let's get back to R. Is on this address, and phew, that's okay. So in the memory, we have secret key, and here's the message. And it's going that way, which means we're potentially leaking memory in this direction. But the secret key is under that. So we're home free, right? So we looked inside. That's what QEMU said. And then we looked in the real hardware. Because on QEMU, when you reach the top of RAM, you just get errors back. But on real hardware, what happens then? So we looked into what happens on real hardware if you hit the top of memory. And what do you know? It wrapped around. Shit! And then it continued. And here's the secret key, remember? So oh fuck! This isn't good. And this isn't a software problem, this is actual hardware translating the address and wrapping it around. So, okay. Kind of bad. But remember R here. And when doing the cryptographic signature ED25, 519, you have some data on the stack during the actual signature. And what we're talking about here in memory is mostly the stack, because most of our memory management is the stack. We don't have heap. So the order on the stack is important here, and this thing that the signature is doing itself changes during the signature, which means the signing itself uses the stack and placement matters. And it's before the secret key, and it changes during the signature, which means we can't leak memory through that point of memory. This is really, really, really good, because an exploit stops here. And the private key is still on that. That's very good, but also very, very scary. So, yeah. The real fix is, of course, to refuse to set the size variable if it's too big. We also guarantee the position of the private key compared to the message to sign. In the C standard, you probably know that this is unknown if it's just variables somewhere on the stack, but it is guaranteed if it's in a struct, and the order in the struct matters. We also fixed the hardware addressing not to ramp the RAM access, and this is from this tag, and beginning with this serial number, that's if you have a T key with a serial number less than this, you are not going to be hurt by this, probably, but you might get unexpected results on some devices, because hardware makes RAM wrap around. And of course, this is our vendor ID, and that's not just a random number. Future of the emulator. The emulator was kind of thrown together for the things we needed at the time of development. It was sort of maintained after the fact, not necessarily during development, as we originally intended. At first, development was done on the firmware first, and then on hardware, then we kind of slipped, yeah. And bringing the emulator up to speed with the next release isn't done yet, for instance, which we would like to. On the other hand, QEMU is large, very complex, a lot of streams, so it's hard to keep track of what they are doing upstreams, and we would like perhaps to find something easier to work with, much smaller and much closer to our real hardware. I mentioned architecture, for instance. And there are several small RISC-V emulators available that we might be able to use. Most of them don't have support for emulating a flash chip, though, but how hard can it be, right? The future of the TKey itself is the next generation. We call it Cascar. It has storage, but it's isolated per app, and we introduce system calls to access those flash areas, which makes our firmware almost like an operating system, and it's doubled in size. Instead of being 4K, it's now 8K. We also have much faster client communication and more USB endpoints. Most notably, a security token like FIDO. So, in summary, we have a USB stick form factor authenticator. It's really a general computer in disguise. It uses measured boot to create unique identities based on the user has, the device itself. The user knows, usually some kind of passphrase, and the software integrity. It's developed with our own fork of QEMU, and the emulator helps a lot, but you need to verify things on real hardware. You might be surprised. Sometimes things are under spec. Sometimes communications between hardware designers and software engineers isn't as good as it should be, and sometimes even hardware designers are surprised at what happens. So that's everything for today except Q&A. You can reach me at mc@tillitis.se and privately on mc@hack.org. We are at an IRC channel called Tillitis on the OFTC network, and which is currently, so far, bridged over to Matrix. You can find our web at tillitis.se, and you can buy stuff on our web shop. And please read our developer handbook. Thank you.
That was really cool. Let's take some questions. Oh, there's one over there, and I will come back.
Hi, great talk. I'm curious what kind of changes and maybe the scope of changes that you had to do to QEMU in order to support your board and development. Like, what's the nature of those things?
Okay, good question. I could probably show code. No, I'm not going to show code. Since our hardware model is mostly memory-based, every hardware core we have is memory-based. The most things we had to do, besides initiating the board itself in QEMU, was the memory management. So we have a switch in a function called read, and another switch in a function called write, and then depending on the memory offset you are accessing with a read or a write, we decide what to do. That's the entire implementation we did, I think. Yeah. So it's basically two functions and a switch in each function and says, are you accessing this memory? Then you redo this. Are you accessing the random number generator? Okay, here's the number 4. We got it from a fair dice. Yeah.
Yes. So you mentioned that the newer versions of the Tillitis key don't make any memory address swapping. Do you have any book reports from software developers saying that you have completely broken the software by changing the way the key behaves?
No reports about that. So far, I haven't found someone relying on that the memory was wrapping. So no such reports.
What are some of the real-world use cases? I mean, this key is, say, different from other keys in that it's much more capable in that it's a full shape, etc. What do you find? I mean, people probably are not telling you, but what do you find the use case here?
Well, I mostly use it for SSH myself, and I think that's the most common use of it. I mean, I open my laptop in the morning, I insert my TKey as SSH to a lot of places, and instead of my private key lying around, hopefully in encrypted form on my file system, or unencrypted in my usual SSH agent, my private key is created on demand and only in my TKey. And then I use it like that for Git, for Git push, Git clone, for SSH to build boxes and stuff like that. I think that's the most usual use of this. So yeah, and so far we are mostly talking to DevOps people, system administrators and programmers. And with the coming generation, with hopefully FIDO support, suddenly people can use it for logging to their webmail or something. And I think that will change some of the use cases. And instead of having several security tokens in your pocket, you can just have our security tokens.
So consolidate for just one token.
Yeah.
Makes a lot of sense. And you rely on hardware, obviously, a RISC-V chip, if I understand correctly, 32 bits. How do you secure the supply chain for that hardware?
Well, the hardware itself, the chip, that's just the lattice ICE40 FPGA. So let me rephrase this. The PCB design itself is done by us, but the assembly of the PCB is done in the factory in Sweden. But then the FPGA is empty, except some test firmware that just blinks the LED to test that it's a real lattice ICE40 and it's functioning. Then it reaches our Gothenburg office, and in an air-gapped environment, we provision it with a real bit stream and the real unique device secret for that particular TKey. And then we close the lid on the entire thing by blowing the fuse inside the chip, and it's not readable anymore, and we also apply the case on it. Yeah, that's sort of the answer you were looking for.
Right, definitely. Terrific. Ah, any more questions?
Yes, you said that you use the application binary to generate the base of the keys that are generated. But then doesn't that mean that if you update the application, you get new keys?
Yes,
Isn't that a problem?
yes. But we have a solution to this problem as well. So the solution is chaining apps. And we've known about this problem and the possible solution to it for a long time. And in the current version, I have a small hackathon project I did last year, I think, which solves this. It loads first an app that is just an imitation of the firmware, implements the same protocol as the firmware, and then loads the second app above it in memory and starts the second app, giving it the same base secret. This is quite insecure if you do it like that. That was a 2-day hackathon thing. But if you also verify the next app before starting it, for instance, by some security policy, you have a public key, you demand a signature over the entire app, verified against that public key, and then start it. So you combine measured boot and not forced, but voluntarily verified boot. Yes, that's the solution. And that's also implemented in the next generation of the Casper I was talking about. And then we get firmware support to do this, changing apps and saying, next app that you are going to start is going to have this exact digest. Please restart. So yes, very good question.
I might have an evil question. So, in my understanding, the anchor of trust is basically the unique device secret.
Yes.
And you just said it is written in the air-gapped environment on the device in your office.
Yeah.
How make you trust me that you do not have for safety reasons, a backup of the unique device secrets?
Excellent question. That's why we also sell the TKey Unlocked, which is empty, and you can provision the bit stream yourself. It's easy to do for most people in this room, I guess. And you can choose the unique device secret yourself, hopefully from a random number generator you trust in your own environment.
Great, thanks.
Have you completely given up streaming your fork to QEMU?
No, not yet. But before we even try to do that, we need to both get it up to date with Castor and also get it up to date with current upstream before even trying to. And we haven't had time to do something like that. We're a small company, and that takes some considerable effort to make it upstreamable. And so we haven't given up, but yeah, I don't know.
Yeah. One more question. Do you use any, or do you have any automated tests, for example, on the firmware or this operating system bootloader part? And do you use QEMU, for example, to run that automatically in CI or something?
We do have a lot of things in CI, but we don't have any QEMU-based tests yet. We want to get to this point. And we also want to get to the point, we also have the entire build, the bitstream build, the hardware design, chip design build in the CI, but we don't have much of for instance, we use Verilator, which is also a kind of emulator, but on the chip level design. And we would like to have that in the CI as well, and run tests against it. But not yet. But yes, we're totally interested.
Well, since we're talking about QEMU and automated testing and upstreaming, maybe those are areas for contribution?
Absolutely. All this is open source, and we are very, very, if you want to help us out, please do. Please reach out, please file PRs, issues, and please talk to us.
When listening to presentations like yours in particular, but also trying to understand simple devices like YubiKey and so on, I almost always tend to get confused trying to follow the stream of here's some secret and here what trusts what, etc. Do you have a good reference? What I could read that kind of describes it in a friendly way?
In general, not for the TKey, but in general.
Well, TKey would be most interested. I would also be interested in YubiKeys, I think.
Well, most of the YubiKey and similar products, some of them at least, mostly trust the black box in form of a secure enclave or something inside them, and they trust that that manufacturer did the right thing. So that's something.
And what I want is some kind of explanation of exactly that in detail, so I can follow it more.
I don't think
what is it I need to trust and what it is I can expect myself. I won't understand it, but I often use it.
It's a very good question, and I'm afraid I don't have any good answers to it. But it's an interesting area. I think we can perhaps find some time to write about it. Follow our blog.
Okay, I'll do.
Trusting trust.
Yeah, exactly. Ken Thompson reference, nice.
So, since you're doing security, have you looked into formal verification of your hardware platform? And how do you handle, if you have, how do you handle it?
Well, I think PKRV32, Clairvolt's softcore RISC-V, is formally verified, or at least some parts of it. But other than that, no, we haven't done anything like that. And there is also the possibility, at least, to do formal verifications of the code. And we haven't looked into that either. I mean, there's Frama C, for instance, where you add some formal comments to your C code and throw it at some solver of some kind and try to verify that what you are trying to do is what you are saying you are going to do. And that's hard, but interesting, yes.
I think I got all the questions. Great questions. Thank you, everyone. Thank you very much, MC. This was really fascinating.
Thanks.